I started the recording. Good afternoon. I think we can start. Let me share the screen. We are a bit late. So, because I wanted to wait for your colleagues, I will teach from now up to 3:30, and then I will make 20 minutes break, and then from 3:50 to 4, yeah, 3:50. Let me just, no, now I'm teaching from now to 2:30, and then 20 minutes break, and then from 2:50 to 4:20, okay, 20 something. Okay, now, we completed the part on forcing estimation for Harbour design. So the next lecture, it's on Harbour oscillations. And in the second part of the lecture, I will again develop the exercise that we started, computation of mooring forces with R. I will do it with R. Okay, now the next, as I said, is Harbour oscillations. So what are Harbour oscillations? Harbour oscillations are a phenomena that may be particularly concerning because it's resonance of waves within an harbor. Resonance means that when you have a harmonic motion like waves, a periodic motion, if the forcing continues, the amplitude of the oscillation may increase indefinitely, and therefore may lead to the formation of very huge waves. For instance, if you consider the pendulum, so let's look at the blackboard, and let me check whether the blackboard is, let's see, yeah, it's here. If we consider the pendulum is the classical example of physics, where you have a mass m, which is handed through a wire to a fixed point, and then if you with the forcing, if you bring the pendulum in a position that is not in equilibrium, like for instance here, you bring the pendulum here, okay, and then you release the pendulum, you get a periodic motion which goes from here to here, more or less. Okay, and therefore you have this movement back and forth. I said more or less here because in absence of any energy dissipation, you get a periodic motion, and it's symmetric with respect to the equilibrium position. So basically this angle here, phi, is the same as this angle here, phi prime, if you don't have any dissipation of energy. And if you don't have any dissipation of energy, this motion continues forever. Okay? Actually, in the reality, you have dissipation. And so you have a slow decrease of the amplitude of the oscillation. And then finally, you get again in the equilibrium position with no motion. Okay, this is something that we know quite well. Okay. Now, let's imagine that any time that you get back to the original position, you again give whatever small impulse of forcing in the opposite direction. So let's suppose that once that you get here at the same time in which you get to this extreme position, let's suppose that you give another small impulse, another small forcing. So if you give the other small forcing, what happens is that you get an expansion, an expansion of the movement of the pendulum. So you get maybe like here, okay? And then when the pendulum comes back, you get to another extreme position here. And now let's suppose that again, when the pendulum stops in the extreme position, you give another forcing, small forcing. It's like a swing, okay? When we play in the public parks with the swing, if any time, at the right time, when you stop in the extreme position, you give an additional forcing, then the amplitude keeps increasing, the amplitude of the oscillation, okay? Okay, and then if I give another additional forcing, you get a continuous amplification of the oscillation. But in order to get this continuous amplification, it is necessary that you get the additional forcing at the right time. Because we know with the swing, the trick, we have to push the swing when it stops in the same position. If I push while the swing is still increasing its amplitude, then it's not effective. So, I mean, the additional forcing has to be done at the right time. And so you understand that the pendulum has a characteristic period of oscillation. This characteristic period basically is what determines the time in which I have to give the additional forcing. And therefore, the periodicity of the additional forcing, if I want to be effective in increasing the amplitude, has to be the same periodicity that is the characteristic of the pendulum. So you must have the coincidence of the period of the additional forcing and the pendulum. And the period of the pendulum is an intrinsic characteristic of the pendulum. So basically, if you want to produce this phenomena, which is called resonance, that leads to an ever-increasing amplitude of the pendulum of oscillation, you have to seek the coincidence of the period of the forcing and the period of the pendulum. Is this clear? This is resonance. So the pendulum is very easy to understand, but you have to consider that any rigid body or body of fluid that is potentially subjected to oscillation have a characteristic period of this oscillation. So for instance, if you think of a bridge, okay, so let's suppose that you consider a bridge over a river, okay? So here you have the river, and here you have the bridge, okay, with the foundations, okay? The bridge is subject to oscillation. Basically, if you give a forcing over the bridge and you bring the bridge in a flexed position, and then you release the forcing, then the bridge starts to oscillate, okay, up and down. So when a car passes over the bridge, in the middle, there is a temporary forcing that brings the bridge down. And then when the car is passed, the bridge comes back with the characteristic oscillation. And you can perceive it because if you are over the bridge and a truck passes over the bridge, you perceive that the bridge goes up and down for a little bit with a characteristic period. And this is another concerning, of course, phenomena, because think of a bridge where a car passes over the bridge with a periodicity. with a fixed periodicity. Actually, this doesn't happen. It doesn't happen because you don't have fixed periodicity in the passing of cars over the bridge. But think of the situation, hypothetical situation, where you have cars passing over the bridge with a periodicity, with a period between one car and the next one, which is the same characteristic oscillation period of the bridge. And then what happens that you have the bridge that starts oscillating and more and more and more and more until it may collapse. And this is a well-known phenomenon, bridge collapsing for resonance. Actually, it doesn't happen in practice because, as I said, the traffic doesn't have a fixed period. But for instance, when the soldiers, they pass over the bridge, you know that soldiers, they are used to walk with a fixed pace. They have to keep the pace, okay? And therefore, they basically walk by keeping the same periodicity in their walking, okay? Between one foot and the other one, they are trained to keep the same periodicity. When they pass over a bridge, they are told to just stop keeping the same pace, and they leave the soldiers free, anyone, of using its own pace, because they want to avoid this unfortunate coincidence of the period of the pace of the walking with a critical periodicity of the bridge. This may happen also in harbors. Think of a wave entering into an harbor. What happens? The wave goes in, and then from the mouth goes into the harbor from the mouth of the harbor, and then reaches the head of the harbor, which typically is a wall. And then when the wave gets against the wall, there is a reflection, and the wave comes back. So the time taken by the wave to travel along the harbor and coming back is the characteristic period of the harbor. It is fixed. It is fixed if in the same condition it's fixed. Of course, if you have different conditions, like, for instance, presence of ships, harbored ships, the characteristic period may change. Typically, it's quite a long period. It's for small harbor can oscillate between 30 seconds and a couple of minutes. This is the typical range of the characteristic period of an harbor. Again, the period is the time taken by a wave getting into the harbor from the mouth to reach the head and to come back. When the wave comes back, if the characteristic period of the harbor is the same of the forcing, of the external forcing, of the external wave, you may have, when the wave comes back, a summation of the waves, which leads to amplification of amplitude, may lead to amplification of amplitude. So what we have to be concerned is the coincidence of the period of the entering waves into the harbor, coincidence of this period with the characteristic period of the harbor. Because if we have the same characteristic period, then it may happen that we have these are called harbor oscillations, which means that you get an increasing and ever increasing amplitude of waves into the harbor. This is what we have to study. And a complication is the fact that the characteristic period of an harbor is not unique. Harbors may have different characteristic periods. And therefore, we have to be aware that we may get into the unfortunate situation in which we have resonance, harbor resonance or harbor oscillation. And these kind of phenomena are also called sage. It's singular and seiches is plural. Okay, so these seiches are anomalous waves resulting from Harbour resonance, from Harbour oscillations. And this is the topic we discussed today. Of course, you already understand that the key to avoid this problem is the estimation of the characteristic periods of the Harbours. Furthermore, you have to be concerned by the fact that the periodicity of these waves may also be the same periodicity of oscillation of Harbour ships. And therefore, because also the ship has a period, a characteristic period of oscillation. If you bring a ship up and then you stop the forcing, the ship comes down, comes back down and up again, goes up and down with a characteristic period. So if the characteristic period of the ship is close or the same as the characteristic period of the waves entering into the harbor, then you may get an amplification of the movement up and down of the ship, which may break the mooring lines or may amplify the mooring forces. So we have to avoid the coincidence of these characteristic periods. Now, let's try to study this phenomenon, which is also fascinating. It's extremely interesting, by first recognizing that this is not a fantasy. It is something that really happened. And it is something that we need to study by understanding how waves reflect back into an harbor after reaching the head, okay, and understanding how these incoming and reflected wave combine, okay. Good. So let me just look at this picture. You see what happens when a wave gets into a wall, gets against a wall that is located at the head of the harbor. So basically, you have a kind of splash, which brings the level of the water up along the wall. Okay. Good. So let me just use the PowerPoint to make a short premise. So usually these oscillations are characterized by quite long period. So the danger is given usually by waves with period ranging from, as I said, 30 seconds to a couple of minutes. These are the order of the periods that are, in a way, may be concerning. And keep in mind that, of course, the characteristic period of the harbor depends on the geometry of the harbor. So it is relatively easy to study it in simplified situation, like rectilinear harbor with the crest of the entering waves that is parallel to the direction of the wall that is placed at the head of the harbor. So if you look from the top, if you look from above, a relatively simple situation is this one, rectilinear harbor, okay? And this is meant to be rectilinear, okay? If it's not rectilinear, it's just because I have drawn by hand, and this is the mouth, this is the mouth, and this is the head, the harbor, okay? And the simple situation is crest of the wave that is parallel to the direction. These are parallel. This is parallelism sign. parallel to the direction of the head of the wall that is placed in the head. So in this case, you understand that the combination of the incoming wave, so this is the incoming wave, and the reflected wave is quite simple. It's quite simple because what happens is that the reflected wave is reflected with the same direction here. So the reflected wave is this one. Okay, and it goes back in the opposite direction. So first you have a combination between the incoming wave and the reflected wave. And it's interesting to study how they combine. And of course, this reflected wave goes back and it reaches the mouth after a period. And then at the mouth, you have again the incoming wave. And the period is the travel time of the incoming wave. This is incoming, plus the reflected wave. Reflected. Okay, and this is period divided by 2, and this is period divided by 2. Is it clear? So you have an incoming wave, it takes half of the period to get to the head, and then the reflected wave starts from the head, goes to the mouth, and takes another half period to get to the end of the mouth. And meanwhile, you have a continuous combination between the incoming wave and the reflected wave. Okay.
So we have just these two to consider.
Yes, and of course, here you have the forcing that continues externally. But inside the harbor, in this simplified situation where you have, as I said, the rectilinear harbor, and the wave crest is aligned with the head, it is a simplified situation because you have only these two waves to consider, and it's a two-dimensional problem because you don't have any change of the superimposition of the two waves in the transversal direction. So basically, if you take a picture along the cross section here of the waves, you take a picture here, you take a section, and you look at, we have several figures, like, let's see. Let me get a figure, just 1 second. Okay, so for instance, this is a composition of what may happen. You can't understand this figure now because I need to explain it to you. But this figure, this is the result of a cross section that is drawn here, for instance. And you would get the same picture of this situation if you drew the cross section here. There is no change in this direction, no change. Okay. No change in the transversal direction. So this is a 2D problem. It's a 2D, okay? Why 2D? Because you have changes, for instance, of the water level. You have changes along the vertical direction, which you don't see here, and along the longitudinal direction, this direction. You have changes. You see that the water level changes in the longitudinal direction. So basically in that direction in the figure, which is this direction here. And of course you have changes along the vertical, because along the vertical you have changes of the water level, but you don't have any change in this direction. So this is a simplification. Conversely, if you had a situation like this one, and just to give you an example, if you had a situation like this one, an harbor that is like this, with the head that is inclined at an angle, and then you have a wave getting here, So the wave is getting into the head at an angle, and the angle, let me indicate the angle, if this is the perpendicular to the head, the angle, it is this one, okay? So alpha, for instance. So the wave is inclined, the crest of the wave is inclined at an angle alpha with respect to the direction of the head. Then the wave gets reflected in the opposite direction with the same angle alpha. So basically, you have a change of the composition of the two waves also in that direction, because then the reflected wave gets again against the side wall of the arbor and then gets reflected again. So you have a complication of the process because you have a 3D problem. You have changes in the 3 direction. In this simplified configuration, we can study the problem as a 3-dimensional problem. B is the period, and it takes half of the period of the arbor to get from the mouth to the head. So this is why, okay, and another half to get back. And of course, let's suppose that we don't have, in this simplified situation, let's suppose that we don't have any energy losses. Okay, so no energy losses. Actually, in reality, the shape of the wave changes along the arbor because there is friction. There is friction against the bottom. There is friction of the wave along the sides. But if you exclude any dissipation of energy, the waves keep the same amplitude, the same wavelength along the arbor. There is no change. Okay. Okay. So what happens in this situation? It's quite interesting, okay? And let me go back. Okay, so these oscillations, as I said, are called seiches and may happen in harbors or in lakes, or they may even happen in your bath tube. If you can originate these seiches, it's quite easy. In your bath tube. When I was young, I used to bath into a tube. Now the tube is no more used. We use the shower, but I was used to bath into the tube. And indeed, I made fun originating these seiches because it is relatively simple. You just have with your hands to give the impulse to water oscillation at the right time. And then I could perceive that the waves increased their amplitude until the tube overflew. And then my mother got, of course, very unhappy of this. And it is very easy. You can also originate these into a glass of water. It is very easy. With a spoon, you can try into a glass of water to match the frequency of the oscillation of the glass with the frequency of the impulse that you give with the spoon to the free surface of the water into the glass. There are several episodes that were reported of seiching into lakes, for instance. There was a famous event that was reported in Switzerland in the Lake Constance in 1549. And also other records were taken because, the waves are originated in a lake by wind. And if the wind forcing is such that the periodicity of the waves, of the swells, matches the periodicity of the lake, then you may have these episodes. Okay, let me just see. Of course, as I said, there are some videos. I wanted to show you a couple of videos here. And of course, the behavior of the phenomena of the resonance in lakes and harbors is different. And I will show you why. Okay, and for instance, another possibility or another possible outcome of resonance is after tsunamis, because the tsunami, you know, it's an earthquake. It originates with the vibration waves, and if the waves that are originated by the earthquake have the same periodicity of the lake or the harbor, then you get the seiches. And let's see a couple of videos. Of course, let's wait for the advertisement to stop. 4 seconds. This is a simulation. It's a numerical simulation of a tsunami. And you see here that the amplitude is constantly increasing, because there is a wave coming back that is superimposed with the wave that advances. Okay, I think this is not very clear. I have another video later that is clearer. Okay, now becomes clearer. But let's pause it and let's sorry, I stopped it. I closed the web browser. Just 1 second. And okay. Okay, good. I wanted to get Chrome. Just 1 second here. Is Chrome. Okay. Okay, good. Now let me just see. I have another video here. Okay, let's see. Okay, here. Okay, this is the characteristic of the wave group. And it's a lab tank. You see that it is a similar situation like ours. It's a rectilinear harbor, but this is not really an harbor because we don't have a mouth here. It's a tank. And at least I think there is no mouth. And the wave is originated with a characteristic frequency by a wave generator. And you see that after the reflection against the head, there is amplification, you see? The amplitude keeps increasing. And this is just because the characteristic periodicity of the tank is the same periodicity of the wave generator. The wave generator generates waves with the same energy, with the same pace. So it's absolutely, you see here, there is no increase of energy by the wave generator, but you see that the oscillation, the amplitude of the wave keeps increasing. And as you see, there is no movement of water. It's an up and down. Now the wave generator is off. But you see that the wave keeps going because in the lab, the friction is very small. And of course, we need to understand how this happens. And this is the task of our lecture today. So what happens when a wave reaches the head of an harbor? Okay. And let me see if there are, I leave to you the task of looking at this video. And let's see, probably at the end of the video, this is a different, I think it's a different periodicity. Okay, so how this happens, let's see. Let me go back without closing. Okay, perfect. Now, let me get the PowerPoint. Okay. So, as I said, keep in mind that a basin may have several natural periods, and these are also called what I called before characteristic periods. These are also called eigenperiods. And these periods are determined by the basin geometry and the depth. This is extremely important. It's also determined by the presence of ships, which may alter the geometry of the harbor. And as I said, in natural basins, this period may vary from a few tens of seconds to, I said, a couple of minutes. It may be also more than that. It may also be several hours. It depends on the size, of course, of the natural basin. In the harbor, usually we don't reach several hours. We don't reach several hours because the time taken by the wave to go back and forth usually is much lower. This is why I said a couple of minutes. But actually, if you study, for instance, a lake may be huge, and it may take several hours for the waves to travel back and forth. And so you understand that the ciphering, the characteristic of a periodicity that lasts for several hours, it's a bit complicated. And the phenomena can be described analytically, but we need, in order to describe it analytically, we need to refer to a simplified geometry, like the one that I'm considering now. Rectilinear harbor with the crest of the wave aligned with the direction of the head wall. Of course, we can also treat more complicated geometries, more complicated situations. But in order to treat a complex geometry, in order to decipher the behavior of a complex geometry, we need a numerical model, not an analytical model. With analytical solution, I mean something that can be written through an analytical relationship and can be an explicit analytical relationship. And a numerical model, of course, it's a possible solution. We have several commercial softwares that may allow us to study the behavior of a complicated geometry, but this is something that it's more complicated. And let me also say that the analytical solution is definitely more useful for educational purposes. So this is why we refer to the simplified geometries. Okay, so first of all, let's make a big difference and look at the slides between closed and open basins. Closed basins are basins that are not in communication with a larger water body. For instance, if you consider a lake is a closed basin. You don't have a mouth in the lake. Of course, you have the outflowing river, but it's not really a mouth. The lake is a closed basin. Okay, an open basin is, of course, on the other hand, a basin that is in communication with a larger water body along at least one side. An example is the harbor. Okay, of course, if the harbor had a very small entrance, then the harbor may be treated as a closed basin. But usually we don't have such situations in harbors. In harbors, usually we have a mouth that is quite large because we want huge, big ships getting into the harbor. And let me say that the size of the entering ships is comparable to the size of the harbor. I mean, the size of the harbor may be like from 10 to 100 the size of a ship, but it's comparable. It's not a different order of magnitude. So the entrance of the harbor should be quite large compared with the geometry of the harbor itself. It's not like a lake where you can have a very huge lake with a very small river outflowing from the lake. So the lake is a closed basin. The harbor typically is an open basin. Good. Now, regarding forcing, we may have free oscillation that occur without an external forcing. And although, of course, some external forcing must have been applied at the beginning, but you may have like a single forcing at the beginning, and then oscillation continue for a long time as free oscillations. Think of an earthquake. An earthquake generates like a forcing that may last for a few seconds. And then the oscillation in the lakes may continue for a long time. Tsunamis usually may occur after several hours from the earthquake, as you may know. And this is a good thing because they can be predicted. So for instance, yesterday we got an earthquake in Taiwan, I think, and then now there is a risk of tsunami in Japan, if I well remember. I read on the newspaper in the morning. So basically, let's distinguish between these free oscillations originated by a forcing that then stops, but the oscillations continue. And given that the friction is generally very limited in these, when dealing with these huge basins, oscillations may continue for a long time. And then we have the forced oscillations, which are oscillation in response to an external forcing that continues. So of course, resonance, you obtain resonance if the external forcing continues. But you will see that even for free oscillations, you may have amplification of the amplitude of the waves under certain conditions. And also keep into account that forced oscillations and free oscillations may combine, of course, because it may happen that you have some forcing that happens and then stops and then starts again, and therefore there could be a combinations. Okay, let's see one thing. The set of periods of seiches are a property of the harbor. So the periodicity of the harbor is a property of the harbor, and it's independent of the mechanism generating the forcing. It's like the pendulum. The periodicity of the pendulum is a property of the pendulum, which is independent of the external forcing. On the other hand, the amplitude of the seiches that are generated depends on the external forcing. So the periodicity of the seiche, it's independent of the external forcing, but the amplitude of the seiche depends on the external forcing. Okay. Now, as I said, we treat the two-dimensional problems. Oscillations are independent of one horizontal dimension, like here. As I said, if you draw a cross shape here or in another position in the transversal directions, the oscillations are independent of the transversal direction. Okay. Note one thing. Okay, of course, we call a 3D problem a problem where oscillations vary in both horizontal dimensions. Note one thing, some textbooks refer to the 2D problem as a 1D problem. okay? Because basically, our problem is to describe the oscillation of the wave along the vertical direction. And given that the wave reproduces itself in this simplified problem specularly, so the wave doesn't change its behavior along the longitudinal direction, the amplitude remains the same and the periodicity remains the same. So some textbooks call this problem here a 1D problem, because they describe the position of the wave along the vertical. So they describe the up and down of the wave along the vertical, and they assume that this up and down doesn't change along the longitudinal direction. I don't think this is correct, because actually the position of the crest of the wave also changes in the longitudinal direction. It doesn't matter if it changes with the same behavior. This note is just to let you know that when you talk about seiches and you refer to textbooks, you may find some textbooks mentioning a 1D problem. The 1D problem is our problem here that we call a 2D problem. Okay, it's just a matter of notation, but I want you to know what are different notations that can be used by different authors. Okay, as I said, the Harbour has a rectangular shape, and I didn't say this before, constant depth. Okay, this simplifies the treatment, because of course, you know, the characteristic of the wave and therefore the periodicity also depends on the depth of the Harbour. So if you have a depth that is decreasing, then also the shape of the wave changes. And you know this because you know what is shoaling, what is the effect of shallow water on the shape of a wave. So let's assume that the depth is constant. So the head is delimited by a vertical wall, and the wave crest is aligned with the direction of the wall, okay? So the wave is reflected perpendicularly and with full reflection, okay? Let's assume that there is no damping of waves, and as I said, no energy losses. Now, what happens in such circumstances? Let's say it by words, and then I will show you a picture. So what happens when the wave is reflected by the Harbour head? The wave is reflected with the same phase, but opposite direction and same amplitude. Let me say again. You get a wave hitting an Harbour head. What happens? You have a reflection of the wave. The wave is reflected in the same direction, of course, with different versions of the wave propagation. Okay, as you see here, the arrow is on the left and here is on the right, but the direction is the same. Same direction, same amplitude, and same phase, no phase change. Okay, one thing here. Here, actually, there is written opposite direction. So let me be clear about that. In some textbooks, they call direction the composition in a vector of direction plus versus. Okay, so basically some textbooks I discussed with a colleague 2 days ago, they call direction of a vector the composition of the direction plus versus. So basically they say that these two vectors have opposite direction. I personally think is more correct to call direction this part of the vector and versus the direction of the arrow. Okay, So I would say that in these two vectors, we have the same direction but opposite versus. But in some textbooks, you may read opposite directions like it's written here, because this was taken by a textbook. Okay, but let's just be clear. I think it is more rigorous to say that the reflected wave keeps the same direction but opposite versus. But as I said, in some books, you may read opposite direction. Okay. But what is important here, and it's more difficult to understand, is the conservation of phase. I think you can easily understand that the wave is reflected with the same direction, with opposite versus. I think you may easily understand that the wave is reflected in full reflection with the same amplitude, because there is no energy dissipation. Okay. What does it mean? The same phase. Okay. Let's try to refer to a picture, and there are several pictures in my website. Let me go back to the website. I'm looking at, okay, closed basin, okay, we're 3D, perfect. Let me get, okay, I think this is the first picture. And let's see what happens here. I think this is, let's look at this picture. I think this is clearer, okay. Okay, so this is our wave, is the incident wave, okay. Then it gets into the head, okay. And then this is the reflected wave. Same phase means that actually the composition of the two waves is here resulting in through to through, crest to crest. Okay, through to through, crest to crest. So what happens then? The through is summed to the through, and you get twice the amplitude. And then you have some points where there is no change in the position. They are like fixed points. Okay, let's go back to the other figure. So this means same phase. Okay. And just keep in mind that this is called free boundary, because the wave against the head of the harbor, against the wall, can go up and down. Okay, it's a free boundary. Like if you take a string and you move the string with from only one side, and you let free the other side. Okay, and let me see. Let's try to see here what happens. So here you have the reflected and incident wave at t equals 0 in blue. So this is the incident wave, which then comes back with the same shape, and the composition is the green one. So basically, if you look at this incident wave, it gets reflected with crest to crest. So this is one crest, and this is the second crest, and the composition is the green one. And then after half of the period, you have the reflected and the incident waves that becomes the yellow wave. So what is the result? The result is what you have seen in the tank in the video before. You have what is called a standing wave. It's a wave with twice the amplitude, with crest to crest, through to through, which means twice the amplitude. And you have some points where the composition of the two waves generates what is called a node, a point that is fixed. This is the composition of the two waves, generating these points that are fixed. And the green one is called standing wave. And so you see that the points, there is no vertical movement with time, are termed as nodes. By contrast, at the antinodes that we define now, crest and through appear alternately. So basically, this is an antinode. Look at my mouse and also the arrow here. And this is another antinode. Okay, I still believe that your understanding may be a bit, not a little bit still confused. And I don't want to take the mathematical treatment for now, because it is relatively easy, and the mathematical treatment indeed describes, after coming to the solution, the green line. But before looking at the mathematical treatment, let me show you another video. So let's see this one. Okay, just 1 second. This is unfortunately 2. Okay. Let me just see if I can take the audio. I don't understand why. Let me see. Don't understand why there is no audio. Let me just check. Sorry?
Of Windows.
You mean?
Windows. This is the computer.
Yeah, okay, but yeah, I think it is. Just 1 second. Let's see. No, it's still not moving. I think. Okay, perfect. Yeah. Okay, thank you very much. I'm sorry, but I'm not used to work with Windows, and therefore, when I have to get, okay.
That matches the length of the string in such a way that.
1 second.
Okay, for this demonstration, I have my able assistant Parker. Parker, smile at your admiring audience. And we will be demonstrating transverse standing waves. I'll also demonstrate traveling transverse waves. Here's a traveling wave. I'm starting the wave by creating a disturbance here with my hand that is perpendicular to the direction of propagation of the wave. So I'll move my hand up and down, and you'll see that the little bump in the spring travels from me to Parker and then back to me again. And you'll notice that when the wave hits Parker's hands, because he's holding it firmly, what was a peak heading toward him converts itself into a valley as it bounces off of his hands. So then a standing wave is where you pick a frequency that matches the length of the string in such a way that the waves created from my side of the string and bouncing off of Parker's coincide with each other and reinforce each other to create a standing wave pattern. The lowest frequency standing wave pattern is this one. It's called mode, M-O-D-E 1, or the first harmonic, or in other words, also called the fundamental mode. It's the lowest frequency mode that you can get in a transverse standing wave. If I double the frequency of that mode, I get the second harmonic, or second mode, and sometimes called the first overtone.
Sorry.
And this one,
okay, you see the node here and the antinode here. Okay.
I don't know if you'll notice, is going twice as fast as the fundamental mode. It has a node that's exactly halfway between Parker and me. And that's a node where there's approximately no motion going on. 2, 1, 2. So now I'm going to try and triple the frequency and get a standing wave pattern that coincides with the third harmonic or second overtone. Let me try again. Okay, I think I've got it approximately now. I think I had it for a little while there. That's the third mode, where the string vibrates in 3 separate segments. There's actually an infinite number of these modes that you can get, and see if I can get one of the higher modes. I think that's 4. And then if you're really, really good, you get 5, 6, 7, 8, etc. So notice that with each mode, there's a particular frequency that I have to vibrate at in order to create that mode. So one-to-one correspondence between the modes and the frequencies. That's standing waves.
Abbiamo
Okay.
portato 190.
Okay, and let's see here.
If you've got a
This
medium
is
and you
very
disturb
long,
it, you
but
can
let's
create a
just
wave.
look
And
at
you
the
can create a
start.
wave in a medium that has no boundaries. In other words, a medium that's so big, this wave basically never meets the boundary, then there's nothing really stopping you from making a wave of any wavelength or frequency whatsoever. In other words, there's not really any naturally preferred wavelengths. They're all pretty much as good as any other wavelength. However, if you confine this wave into a medium that has boundaries, this wave is going to reflect when it meets the boundary, and that means it's going to overlap with itself. And when this happens, you can create something that are called standing waves. We'll talk about what these mean in a minute, but the reason we care about them is because when standing waves happen, they select preferred wavelengths and frequencies. Only particular wavelengths and frequencies are going to set up these standing waves, and what ends up happening is that these often become dominant, and that's why these standing waves are important to study. So let's study some standing waves. Let's take a particular example. Let's say you've got a string, well, not that many strings, one string here, and you nail this string down at both ends. So you're going to prevent any motion from happening at the end of this string. The string can wiggle in the middle, but it can't wiggle at the end points. And this isn't that crazy. A guitar string is basically a string fixed at both ends. Piano strings are strings fixed at both ends. So the physics behind standing waves determines the types of notes you're going to get on all of these instruments. And by the way, this point over here, we're basically making sure that it has no motion. So by nailing it down, what I really mean is that there's going to be no motion at this endpoint and no motion at this endpoint. And instead of calling those no, that disturbance is going to move down the line because that's what waves do. It's going to come over here. Once it meets a boundary, it's going to reflect back to the left. Now, it turns out when a string hits a boundary where it's fixed, when it hits a node, in other words, it gets flipped over. So you might have tried this before with the hose. If you send a pulse down the line and you try to see how it reflects, it gets reflected upside down. That doesn't matter too much for our purposes, but every time it's going to reflect, it flips its direction and it keeps bouncing. Now let's say instead of sending to the left, now it turns out when a string hits a boundary where it's fixed, when it hits a node, in other words, it gets flipped over. So you might have tried this before with the hose. If you send a pulse down the line and you try to see how it reflects, it gets
You see that this is a situation which is not our situation. This is a situation with the fixed hand of the string, while the wave corresponds into an arbor to a moving hand. When it reaches the head, the wave can go up and down. So it's not a fixed head, and not a fixed hand. So when you have a fixed hand, the reflection is same direction, same opposite versus, same amplitude, but the phase is switched 150 degrees. So basically you have through against crest. When you have the moving end, there is no phase change, okay? And it's a different situation. In the Harbour, basically we have a moving end at the head. And we will see what happens at the mouth, okay? And now, let me see. I think, I'm not sure whether there is the situation here with the moving end. So you see this video is quite long, so I suggest you to have a look because it's very clear, but I don't want to look at it now. I don't remember if there is the case here of the moving end. No. Okay. Now, let's look at, I think there are other figures here. So now we can look at this figure. This figure is free boundary, free to move at hand. It's our case. So we have crest to crest. And this is indeed the fixed boundary. And you see that there is opposition of phase. Okay, and now you can see here our case. This is our case. So you see here that the boundary is moving, and here it's simplified. So basically you have the incident wave, the reflected wave, and you see the result here. The lower figure is more understandable with respect to this one, but you can also look at both of them. It's the same situation. So this is the head of the Harbour. And you see that why it's called a standing wave. Look at the black line, because it's not traveling. It's a wave that is completely standing. It's the composition of the incident wave and reflected wave that basically it's generates a wave that is not traveling, it's standing. It's standing. It's standing also during time because it lasts for a long time if there is limited friction. Now, this is what happens at the head of the Harbour and why there is conservation of phase. There is conservation of phase. I think that you studied reflection with Professor Archetti, and we took an agreement that she would teach reflection, refraction, and diffusion of waves. So I'm not teaching them anymore. But basically, in order to study the reflection, if you impose that at the head of the Harbour, there is no horizontal movement because the head is fixed, the reflection takes place with conservation of phase. So basically you have at the head of the Harbour twice the wave amplitude. Why is that? You understand from the figure here, the first figure. You understand why you have twice the amplitude of the wave, you see? Because while hitting against the wall, there is no possibility for the wave to travel anymore. So the energy of traveling turns into energy towards the top. And therefore, you have a duplication of the amplitude. If you imagine what may happen with a similar wave at the mouth of the harbor, it's a completely different situation, because at the mouth of the harbor, basically, the wave that comes out from the harbor doesn't have any possibility to influence the depth of the ocean. It's communication with a larger water body. So the larger water body is not influenced by the energy that the waves that come from the harbor. So basically, you have a fixed end at the mouth of the harbor. The end that is determined by the larger water body. So you have these waves traveling out of the harbor, and they reach the larger water body, and it is a fixed end. It is fixed because it is determined by the level of the larger water body. So you don't have this phenomena here of the wave that climbs up, because the wave from the harbor gets into the ocean, and it's the level of the ocean that makes the rule. And so it is a fixed end. So let's think of the situation where the ocean is calm. You have the wave originated inside the harbor for whatever reason, and when they get to the mouth of the harbor, they don't trigger waves into the ocean. The ocean is like a fixed end. So the phase is not concerned, but you have a reflection with the opposite phase. Like you see here. I go back to the figure. You see that at the mouth, you have a fixed end. The wave basically doesn't change its position because it's fixed. So this is what happens into an harbor. And before we pass to the mathematical treatment, which we may discuss in the following of the lecture, we have to be concerned by the fact that there are several characteristic periods, and the video with the two persons showed you very clearly that. So there is one characteristic period, which is let me just. So let's suppose that this is the head. Okay, and this is calm sea. And this is the mouth. So you have one characteristic period that is this one. So this is basically the fundamental, the longest period is called the longest period, the longest characteristic period of the harbor is called the fundamental period. This is the fundamental period. Okay, and the other side you have this. Okay, and this is P divided by 4. This is the fundamental period, and then there is the second period. So you have no nodes inside the harbor here. The only node is in the mouth, and then there is another fundamental period that is going to change. Another period, which is not the fundamental period, which is this one. Okay. Let me just okay. There is only one. There is one node here, and so I think it is Okay, let me wait for this. Let me just look at here. So let me look at this figure because I don't want to make, so if, okay, perfect, it's here. It's not yet below, but it's here. It's here. Okay, this is only one node. And then there is this figure here with 2, 3 nodes. So what I drew over the blackboard is like this figure here if it was truncated here in the position of the mouse. So we have to understand how to describe these periods. Okay, let me introduce the mathematical treatment before we make the break. So let's call let me see if in the PowerPoint I have some. Okay, let's describe it here. So the standing wave is called WS. WS is the position of the wave along the vertical, depending on time and depending on the longitudinal direction S. And the WS is the sum of the incident wave, WI, plus the reflected wave, WR. Now, we can describe the incident wave with a cosine function. And basically, we can describe it as wave height divided by 2, which is the amplitude of the wave. Okay, the wave height is the distance between crest to through, and it's twice the wave amplitude. Okay, and so we call the wave height capital HI divided by 2. And we multiply the wave amplitude by the cos function, the cos of 2 pi, which multiplies x divided by L minus t divided by t. So as t progresses, depending on t and depending on x, you get the shape of the wave at a given time and at a given position in the longitudinal direction. So if you keep, for instance, x fixed, let's suppose that x is equal to capital L. So L is the full length of the Harbour. Okay, so let's suppose that x is equal to capital L. So we study what happens at the wave in the correspondence of the head. Basically, you see an up and down depending on time, and time, basically the wave repeats itself after each period, capital T. So basically at the head of the Harbour, you see that there is an up and down. Okay. Now, the reflected wave is the same wave with, of course, you have to put a plus sign here instead of a minus. And if you make a composition of the two waves, basically you get that the composition is gives a wave of amplitude that is given by the sum of the amplitude of the incident and reflected wave times cos two cosine functions, which can be obtained by the summation of these two cosine functions here with a simple trigonometric transformation. And what you get is indeed a standing wave. Now, this can be done also with an R code. And in the next hour, we will make the case, we will provide an example of an R code that allows you to compute these functions, these trigonometric functions. Okay. Let's make the break. Do you have any questions so far? I am aware that this treatment is a little bit complicated. At the end of the lecture, I will tell you what are the questions that you may expect at the exam, okay? And but by the way, not this mathematical treatment. The mathematical treatment is just to give you an idea of what happens, okay? And here you have a change of sign because the wave is traveling in the opposite direction, but the phase is the same. I mean, you have to change the sign because in order to change the versus of the traveling, but the phase remains the same. You have a conservation of phase here. Okay. I think we can meet in 20 minutes from now. Okay, perfect. let's try to better understand this mathematical treatment, okay? Because it is very simple, but of course, equations are simple if you try to apply them. If you just look at them, they are never simple. So let's try to apply these equations. So first of all, let me get the equation of the incident wave, okay? W I is equal to, okay, it is called H I divided by 2. Again, this capital H is wave height from crest to through. So it is twice the amplitude. If you divide the wave height by 2, you get the amplitude. Okay? And then we get cos of 2 pi, which multiplies x divided by L minus t divided by capital T. Capital T is the period, L is the length of the arm. So if we have the arm here, okay, this is L. This is the x direction. This is x. So this is 0. X is varying from 0 to L. Okay. And it takes a time t equal to half of the period from mouth to head. From mouth to head. Okay. So, first question, what happens at the mouth? At the head, sorry. What happens here? So in order to study the head, I need to study what happens for x equal to L and t equal to half capital T, correct? So if I want to study the height of the position of the incident wave at the head, I have to apply the equation for x equal to L and t equal to half of the period. Okay? Because the period is the time taken by the wave to go forth and back. Okay, so let's apply this equation. W, let's call it W E equal to capital H I divided by 2 cos of 2 pi, which multiplies 1 minus 1 half. Correct? Because here is t divided by 2, t divided by 2 divided by t is 1 half. Okay? So basically this is equal to hi divided by 2 cos of pi. Okay? Or minus pi, no, it's pi, it's pi. Okay, this is the incident wave. Okay, a reflected wave. Reflected wave is the same formula. WR is equal to HR divided by 2 cos 2 pi x divided by L plus T divided by capital T. Okay. And again, I substitute x equal to L and t equal capital T half, so WR. Any question? Sorry, this is, yeah, it's okay. Okay. WR is equal to HR divided by 2 cos of 2 pi 1 again plus 1/2. So it's equal to HR divided by 2 cos of it's I think this is 3/2 divided by 3 it's 3 pi, correct? Cos of 3 pi. Yeah, I think it's 3 pi. Let me just, it's 1.5, 1.5, yeah, 3 pi, okay? So, okay, let me write here. This is equal to, cos pi is 1, so this is hi divided by 2, and the cos 3 pi is equal again to 1, correct? Because it's pi plus 2 pi. So it's again 1, so this is HR divided by 3. So what did we find? We found that at the head, I have to sum incident and reflected wave. And given that we have full reflection, HR is equal to HR, I just have to double the amplitude. This is what happens here. It's a free, and so the amplitude is twice the amplitude of the incident wave.
So you want to prevent this, right? Or you just.
No, I don't think, not necessarily. I mean, once that you get a wave that has the period that is corresponding to the period of the day, this happens. If you want to prevent this, you should avoid a wave which has a period that has the period of the Harbour. Okay. But actually, in any case, when you generate a wave against inside an Harbour, you have full reflection, and and you get a standing wave in any case. Okay. But in order to get a standing wave, you have to match the two periods. Yes, you have to match the two periods.
I say the double I maybe it's no, it's maybe it's 19 HI divided by 2.
Okay. It's when you sum. Okay, you have this equivalence. Okay.
Yeah.
And sorry, say again.
It's a 90.
It's
90. Yeah, it's you can say this must be.
no, it's not opposite sign, because it's not an opposite sign, because the cos of pi is okay. I understand what you mean. It's -1 indeed. It is -1, and but it is the same. It is the same. Yeah, but it is correct what you say. I didn't write it here, and probably it's correct. Yeah, because pi is minus. Yes, correct. And then, of course, when time progresses, so we have the sum of the two minus for time equal to capital T divided by 2. But the next, after the next period, you have, of course, here it's the time is equivalent to t plus t half. So in the next period, you have this time that progresses, and then you get the up the wave, and then you have the phase up. Okay, but you are correct. Here it's a negative sign. Okay. Now, so as time moves, basically you describe the wave, the up and down. So basically, when you have the next half period, you get the up of it. Okay. So in the first period, you have the down because the equation is written in this way. And written in this way, of course, in the first half period, you get the down of the wave. And then in the second half period, you get the up of the wave. I hope it is correct because I made it a little bit on. Do we understand? Because we get after half period the through of the standing wave, so the down. After another half period, you get the up of the wave. Okay, now what happens here is things. What happens at the mouth? Okay, if I want to see what happens at the mouth, I have to put x equal to 0. So basically, if I want to start at the mouth, x is equal to 0, and time, I mean, let's put time equal t. Time equal t. What happens at the mouth after a full period? Okay. So here I have, allow me to make the correction directly on the blackboard. 0 here. Minus, so basically here it's 0. And here is minus 1. Minus 1, correct? Because t is equal to the period, so yeah, minus 1. And then you have here cos of minus 2 pi. And the result is cos of minus 2 pi is 0, the result is 0. Correct? At the mouth. Because it's cos of minus 2 pi. Cos of minus 2 pi is 0, correct? Because it's a full. I would say no, because 2 pi is a full circle, correct? So minus and the cos of 0. Yeah, sorry. It's the cos of 0 is 1, but then when I got okay, is 1. Sorry. It's 1. So cos of minus 2 pi is correct, is 1. So it's I2 again. So this is basically the description. Yeah, correct. Is cos. Okay. So now let's do the same here. It's I think let me just see 0, okay, and here I put again plus 1. It's t divided by t. So this is 0 plus 1 cos 2 pi is 0. Okay, so let me just think. And then here it's okay, let me just write also here 0 plus 1. And this is cos 2 pi. And this is HR divided by 2. Let me just check if everything is correct. So it's 0. Perfect. And I was thinking of, yeah, because those times. So there is again the summation there. Why is that? Let me just, I was expecting here to get a node. So basically, this description is a description of two, it's not our description. I think here, this is a description of a closed basin with two heads. And in order to impose, and then we get also at the other head. So this is a mathematical description of a basin with two heads, not with a mouth. So if we want to put here the description of the mouth, we have to change here the time in, we have to change the time here, and I think we should put here the period of the day is twice. Yeah, I think we should put a 2 here in the description. And then, or which is the same, the time shouldn't be, should be t half. And here t half, and t half. This is the mathematical description of the mouth here and the head here. So basically, what is written there is the mathematical description of the closed basin, not of the open basin. In the open basin, you have to change here the phase. Okay, and if I make the computation here, I think that we should get it. I think we should get it. And but anyway, let's assume that this is the description of the closed basin, okay? And let me see. Yeah, it is a description of this one, of this figure here. I'm sorry that I made the confusion at the beginning, but it is the description here. If we want to get the description from here, I think we have to correct both the arguments here. We have to change the L and change the period, because it is, we need to make a transformation of the trigonometric function. Okay, now we already discussed this. Let me see if we already saw this video. Just 1 second.
Turn on the change. Addio acqua in bottiglia. Benvenuta acqua filtrata. Turn on the taste.
I think, yeah, I think it's the same that we saw before. Yes, sorry for that. We already saw this. Okay. Okay, now, let's now study how we can estimate the natural period for basins, for harbors. First of all, here there is an interesting Wikipedia page on a collapse of a bridge, the Tacoma Narrow Bridge, in its opening day. And you see that they made a celebration for the inaugural ceremony, and they basically organized the celebration in order to pass several cars at a regular distance. This is what can cause resonance. And I think there is a nice video here.
one of the fundamental jobs of an engineer
I
is to
found-
compare loading conditions to
It's a
restraints.
bit too long,
If the
but
loads exceed the certain
we
scenario,
need to
you've got a
skip
problem.
this introduction.
Buildings and other structures face a huge...
Let me see.
This video is sponsored by the Great Courses Plus. More on that later.
Just 1 second.
A bridge. In July 1940, the Tacoma Narrows Bridge opened to traffic between Tacoma, Washington, and the Kitsap Peninsula. At the time, it was the third longest suspension bridge in the world. Financing construction of the bridge was a major obstacle, which led the state to pursue an innovative design. Not that the bridge was too flexible, even
It is
under
reporting the history of the
construction
bridge,
workers
but
gave
let's
it
go to the
nickname
video.
Galloping Gertie. Only 4 months after it opened, the bridge collapsed with helical veins to create turbulence vortex shedding. You can see this in the vertical undulations for which the bridge was famous. But this resonance isn't why it failed. About 45 minutes before failure, a different kind of oscillation started.
Just 1 second.
Footage that right before failure, the bridge isn't oscillating vertically, but in a twisting or torsional motion. The reason for this change in oscillation is still debated, but one of the best suggestions has to do with the aerodynamics of the bridge.
Ti piace Netflix? È il momento giusto per averlo con Sky a un
Sorry,
prezzo da urlo.
this,
Le serie e gli show di Sky. E in più...
Rather than a truss through which wind can flow, the shape of the Tacoma Narrows Bridge with the large steel plates on either side.
just
One way that modern bridges avoid flutter is to include a gap, and the bridge failed.
impressive. I mean, what can happen with the resonance?
One way that
Impressive.
modern bridges avoid flutter is to include a gap in the center of the deck so that the pressures on either side can equalize. I cut a slot in my model, and sure enough, the vibrations almost completely stopped. Another option is just to make the bridge
Okay.
deck more aerodynamic to avoid creating vortices that push and pull on the structure. Of course, bridges aren't the only civil.
Okay, so how can we estimate these periods? And let me go back to here. Mhm. Okay, so it is there is the visualization which is not good. Okay, let me just anyway. I think we can stay here. So there was first attempt to describe the natural period for closed and open rectangular basins with length capital L and depth capital D, which, as noted above, is supposed to be constant. The depth is assumed to be constant along the basins under the assumption of absence of friction. So the formula for closed basins is known as the Merian formula. By the way, please remember this this formula. And it is one of the things that I kindly ask you to remember, not the mathematical description here, which, by the way, next time I will revise a little bit to give you the formulation for the open basin, okay? But you don't need to remind this. And what is important that you remind this formula, because it is also quite let's say, intuitive. And again, this is for closed basins. So this formula was computed, derived to analyze the situation that you may find into lakes. So you see that for closed basins, the formula basically is obtained by putting at the denominator twice the length of the basin, because twice the length of the basin is what we want to. It is the length of the travel ahead and back. Okay, so it's the distance covered during the period, twice the length of the basin. Okay, and at the denominator, you see the square root of the product of the gravity times the depth. What is this quantity at the denominator? This quantity is the celerity of the wave. It is basically the velocity of propagation of the wave. It's the celerity. And so if you divide the distance by the velocity of propagation, you get the time taken by the wave to go ahead and back. And why do we divide by lowercase n? What is lowercase n? It's the number of nodes. Remember, you are in a closed basin. So if you have just one node, the node is, looking here, look at here. The node is, the presence of one node is splitting the, 1 second. This is, okay. This is the situation in a closed basin. And if you get the presence of one node, basically you have two full cycle of waves, two full periods to cover the basin. Okay, and therefore you have to, in a way, to divide the distance by the number of the nodes to get an estimate of, let me go back to the Marian's formula, to get an estimate of the natural period. The natural period depends, of course, on the number of nodes. You have seen the video of the string. If you put several nodes, if you put one node, for instance, the period of the wave is split by 2. So if we get here to this first video, you may remember that
Se resto protegge fino a 8 mesi da pulci, zecche e dal rischio di leishmaniosi nel cane. Allaccia la libertà. Oggi con Enel hai una nuova offerta formidabile. Se sei già cliente luce o vuoi diventarlo, con formidabile
so in this
So
case,
then a standing audience, and we will be
this is like a closed
demonstrating
basin, okay?
transverse standing waves.
Similar situation.
I'm
And
starting the wave by creating a disturbance here with the motion of the wave. So I'll move my hand up and down from me
in this
partner,
case,
and then back to me again. And you'll notice, and then back to spring.
sorry, I'm not.
So I'll move my hand up, peak heading toward him. So then a standing wave is where the waves created and reinforce each other to create a standing.
Okay, here we are.
First harmonic.
This is no nodes.
In other words,
you
also
see?
called the fundamental.
And look at the period. This is the fundamental mode with no nodes. Now, if you put one node in,
harmonic or second
you see
mode,
the period is up.
Sometimes called the first.
So you have to divide by the number of nodes
And this one, if you'll notice,
if you
is
want
going
to
twice
get
as fast
the characteristic
as the
period.
fundamental mode.
And here you have 3 nodes.
Standing wave pattern. Let me try again.
So you see that if you have here you have 2 nodes.
Okay, I think I've got
and you see that the period is
I think I had it for a little while there. That's the
Still
third mode.
lower.
Where
Okay. So basically, if you go into the Merriam's formula here, by considering the case with one node, two nodes, three nodes, you get the different periods of the basin, of the closed basin. Okay. And this basically tells you that you have different characteristic periods depending on the number of nodes. And so this is for instance, this is the picture, closed basin. This is the fundamental node with the fundamental mode with one node. And this is what may happen in a closed basin with one node. So basically you have half of the length, and then you, with the Merriam's formula, you put a lowercase n equal to 1 here, and then with the Merriam's formula, you get the period of this fundamental node. This is for closed basin. Second mode, two nodes. So you use Merriam's formula, and you put lowercase n equal 2 here. Perfect. Now, third mode, third harmonic. Okay. Now, what happens in an open basin? It's our case. So once again, remember this formula because it's quite intuitive. Twice the length of the basin for a closed basin, twice the length of the basin, divided by the celerity, velocity of propagation of the wave, divided by the number of nodes. And the number of nodes is at least 1, because look at the closed basin. This is what happens. You have 2 free ends in a closed basin, and you get 1 node. Good. Now, open-ended basin. This is the situation. You may remember that I drew this situation on the blackboard before. So this is the fundamental mode with no nodes, because actually you have only one node, which is at the mouth of the basin. It's here where is my mouse. Okay. So you can apply Merriam's formula still, but you have to modify it. And keep in mind that if you also the wavelength is, in this case, is half of the wavelength in closed basins, because an open-ended basin is like half of a closed basin. It's like half of a closed basin. And then this is the second mode. Also, this is what I pictured over the blackboard. And this is the third mode. Again, this is our case of the Harbour. How can we modify Merriam's formula? Like here. We need to impose the presence of a node at the open end. And then this is what we need to do. And the period for the fundamental node, and with only one node at the end, it's this one. So, I mean, if L is the length of your Harbour, you take 4 times the length of the Harbour. You divide it by the square root of the product of gravity by the depth, and you get the fundamental period of the Harbour. Okay, let me write it on the back. So the case of, you see how the Merriam's formula is modified. In the same way, we should modify this. And next time, I will give you the modified formulation for this analytical interpretation. Okay, let me just quick sketch here. So this is our name. Harbour. Let's call the length here and like I did before, okay? So what happens, this is the head. This is the mouth. What happens for the fundamental node? Let me just show it here in cross section. So I have only one node at the mouth and an open hand. So the wave is like this. Okay, so what is the distance that is covered by this wave in a full period? The distance, let's call it L star, is equal to 4L. Because in the distance of L, in the distance of the wave, you have just 1/4 the wave period, because then you have to go back to 0 and then there is the lower part. Okay, so what is the period then of this wave? The period T is equal to 4L divided by GD. Okay. Okay. And this is Marian formula for open basins. And then if you put one node, then it becomes like this. It becomes like this, and then you can use the modified version of the Marius formula to compute the other periods. This is the fundamental one, and then there are the other periods. Okay, now, of course, this formula, it's a first indication. It's a quick and easy estimation of the period of a bay, and it can be used to derive an initial value, a trial value for the period. And of course, it is derived under very simplified assumptions. And therefore it is, I mean, it is something that it may provide a rule of thumb, a first indication. If you want to get a more precise estimate, then you have to consider what is the specific geometry and what is the interaction of in the 3 dimensions of incoming wave and reflected wave, and therefore you need a numerical model. But in order to get a first indication, this is something that you can use. finally, there are additional references that are provided here, which you may want to inspect. So there are some links. Like I'm just checking if everything is still alive with the links. And here, for instance, there is an illustration of what may happen in lakes, and after the effect of wind. So it is the wind forcing that may create a displacement of waves. And then there is a second link here. And I mean, it is the same thing. Let me see. Okay, I think here there is. Okay, and let me just see here. 1 second. Okay, and this is another discussion of what may happen in closed basins, actually. Now, what should you remember here? So first of all, just for preparing your exam, just remember the Merriam's formula, and be prepared to provide a description of what is a standing wave, which generates from the superimposition of an incoming and reflected wave. And just try to be prepared on what are nodes, antinodes, and what is the difference between a closed basin and an open basin. So in a closed basin, you have two antinodes at the two extremes of the basins. In an open basin, you have a node at the mouth and an antinode at the head of the basin. So just try to be prepared to describe these features in a qualitative way. The only quantitative thing that I suggest you to remember is the Merriam's formula, and for closed basins and for open basins. And meanwhile, as I told you, next time I want to make clear here the analytical derivation to specify what is the reference, meaning that this is for a closed basin, and I will provide also the analytical description for the open basins, just for your clarity.
Sorry, you said for closed basins, antinode, we have just antinodes.
Yeah, in closed basins, we have two antinodes, a node at the mouth and an antinode at the head. I think there is here an R code. Just 1 second. R code. Okay. Okay, let's. I am opening an R console because I want to show you how we can generate into R by using the analytical formulation that I gave to you. How we can generate a standing wave. So let me just see. Let me open an R console. 1 second. Okay, here we are. Okay, let me change the font. Okay, I clear the screen. So let me get the code here. So this is basically a code. Let me try to cut and paste it first of all, and let me just see. The plot is plot, okay, reflected wave, okay. Let's do like this. Okay. Now, I make a cut and paste of a plot of the calm conditions. You see here that there is the head, and here there is the mouth. Okay, this is for calm conditions. Now, let's okay, calm conditions. Now let's look here. Okay, and let me see the plot. Okay. Let me just. Okay. One second. Okay, here is the wave. Okay, let me do like this. And this is the reflected wave. But you see here that, let's repeat it. Okay, basically there is the start with the calm conditions. So let me, okay, calm conditions. And this is the plot with calm conditions. And then there is a cycle which makes the simulation of the propagation of the wave. So let me see here. I think okay. And this is the propagation of the wave. And this is the incoming wave, which gets in. And keep into account that in this case, we have the situation where in the open end, we assume that the forcing continues. So there is the ocean, the large ocean is keeping oscillating. And because this is the situation that I presented at the blackboard, and which doesn't imply the presence of a node at the mouth because the ocean is still continuing to oscillate. And this is why it is a situation that is like in the closed basin. And then we can here make, sorry. No, this is not, sorry. Okay, and this is the effect of the reflected wave. So basically, when you have the reflected wave going back, you see that indeed you get the situation that we expect from the open basin. This is the reflected wave. And this is generated with this simple code into R. One second, I want to see. So this code, it is understandable from you. These are the data. The data is just the amplitude of the wave, the length of the bay, and the velocity, the celerity. And here, the plotting calm conditions, it's trivial. Just look at the situation, at the instructions here. And then there is basically here an instruction that gets the system time in order to give the animation. So as the system time progresses, we get the wave propagating. So the function system time is getting the time from the system, from the PC, so that you have the propagation. And in fact here, for the incoming wave, you have the animation as the time progresses. Okay, I didn't delete the plot that was before, but you see here, as time progresses, you have the propagation. And this is the incoming wave. So this is the situation after half of the period of the bay. Okay, and then from here on, there is the reflected wave that is going back. And then you get the superimposition. Okay, and good. And then here you see that there is, let me see this again. We have to wait for the cycle to finish, but then at the end you see the superimposition of the two waves. Okay. I would say that here, okay. I'm still have one doubt here. I'm sorry that I didn't notice that before, and because I need to make a correction of this formulation, because indeed, in this way, I was expecting that this was the formulation for the open basin. Instead, it is for the closed one. I'm sorry, I didn't realize it. But I will make the correction, and next time we will discuss it again, because I don't want to leave something that is obscure. Okay, perfect. Beside this, do you have any question? Okay. It's here. It's in the page code. With our software, you may want to cut and paste this code. Okay. Good. Just 1 second. I think. I'm just giving some additional thought to this. Just 1 second, because indeed, this is the period 2t. Okay, let's just try to clarify this, because I prefer to try to clarify it now. So let's see if indeed these equations need to be adapted and how we can adapt them. Okay, I think this may help us in clarifying what is still obscure. So let me write these two equations again. Okay, so it's Wi X. I want to write them one after the other. So it is I divided by 2 cos 2 pi, which multiplies x divided by L minus t divided by t. Let me see, everything is okay, perfect. This is one. And this is the reflected wave. X. I think, yeah, I think I understand what was my mistake for H divided by 2 cos 2 pi. And then here I have x divided by plus t divided by 2. Okay, good. Okay, so now let's study x equals 0 and the time t equal to t. Let me just think of it. Yes, t equal the period of the day. Okay, good. And so we get W I 0 capital T is equal to H I divided by 2 cos of 2 pi 0 minus 1. Okay. So this is equal to H I divided by 2 cos minus 2 pi, which is 1, correct? So it's H divided by 2. Yeah, otherwise, in order to get 0, we should have okay. Okay, and then we get here WR X is equal to it is HR divided by 2. Okay, also it is still 2 pi, right? Because here we have 0 plus 1. 2 pi, which is equal to is minus 0, which are divided by 2. Okay, so in order to get a node here in this HR, in order in this situation we have yeah, this is the 1 and yes, okay. So in order in this situation we have the summation of this. So basically what you get as a result is H1 plus 2 plus divided by 2 plus HR divided by 2. And this is the result. In order to get a node here, we should have got 1 minus sign instead of a plus here. So basically what we should do is, in order to put a note there, we should get here cos pi instead of cos 2 pi, because cos 2 pi is again 1. Cos pi will be -1. So in order to get here cos pi, I think it's the period that should change. So basically, the reflected wave, I think probably, so if we get 2 here, this becomes pi. But if we get a 2 here, we should get also a 2 here. So it's okay. Let me think about it because I can't. Indeed, this is the reflected wave. Okay, okay. The reflected wave. Yeah. I think we need a shift of time because when the incident wave is starting from t equals 0, the reflected wave is starting from t not 0, but after half of the period. So this is why we need to make a shift of time for the reflected wave, because they don't start at the same time. The incident wave starts for instance, from now. The reflected wave starts when the incident wave reaches the head. So basically, here it's this is should be t minus not minus, but it should be, this start later, so it's not the same time. Here we have to put a t star, and the t star is equal to t plus half of the period. So basically, we need to make a substitution here. And t star, and then if we shift the reflected wave out of the period, we get the correct result, which I think it is what is done in the R code. I need to check because I did this code 1 year ago, and in the R code, if we go to the R code here, you see that at the end of the simulation, we get a node here at the mouse, which is fine, and an anti-node here, because the reflected wave starts later. This is why how this should be adapted. I'm not sure if I was clear in my explanation, but the trick here is that the reflected wave doesn't start at the same time. So basically, what we should compose is the reflected wave must be computed for time t star. So basically here I should put t plus, yeah, I think this works. I think this works. I think so, but I will, okay, next time I will clarify this and I will make a correction also in the web page. Okay, good. Now, given that we have this R window open, let me take the opportunity to go back to our exercise, computation of wind actions on a moored ship and computation of mooring forces. So, you may remember that we already make this computation until the computation of the wind force, and we did it also in Python. Now, let us look at how, given the wind force, which is applied in the center of gravity of the wind edge area, let's discuss how we can compute the mooring forces. First of all, we need to compute the rotational moment. The rotational moment is obtained in a very simple way. We take the wind force that we have computed, and then we need to compute the rotational moment by multiplying the wind force by the eccentricity. Eccentricity of what? Of the center of gravity of the wind edge area with respect to the pivot point. The pivot point is the point to which the ship naturally rotates around. Okay, the vertical axis around which the ship naturally rotates around. Of course, the position of the pivot point is not coincident with the center of gravity of the wind edge area, is not coincident with the point of application of the wind force, and therefore there is a rotational moment. And the rotational moment, again, in order to compute the eccentricity, we need to take the length of the water line and multiply it by the coefficient C XYW, which is eccentricity coefficient. So basically, we take our ship okay, like this one, and here there is the water line. So let's take the rotational axis, which passes through the pivot point. This is the pivot point, okay? And then there is the center of gravity of the wind edge area, which is here. And this is the eccentricity E. So the wind edge forcing is applied here, okay? And in order to compute the rotational moment, we have to compute the product between the wind force times length water line times the eccentricity coefficient, XYW. Let me see if the symbols are the same. XYW, yes, length water line. Okay, and this is E. And this is the rotational moment and W. This is quite simple because this is given in our data, and this is also given in our data. So we can compute the rotational moment in this way. This is quite simple. Okay. Let's get the code. The code is here, as you may remember. And we got up to here. Computation of the wind force. Okay, so let me copy and paste this. One second. Okay, let me do like this because I wanted to write a function. So let me computation of the wind force. It's here. 1 second. Okay. Okay, now we can make a return py, and we close the 1 second. Okay, here. Okay, PW is y return PW. Py, like this. 1 second. Okay, moorings. Okay, and this is our Py. So what I did here is to write a function into R, which basing on these default parameters, which are the data that I need, computes the wind forcing. And this is what we did last time, okay? And I completed the function by giving the instruction of giving back to me the amount of the wind force. And then when I run the function, I get the wind forcing. And this is what we did last time. Now, let's compute the rotational moment. Okay, so I go here, and then this is the computation of the rotational moment. Okay, positive clockwise. So I am copying and pasting here. Now, here, the function is not completed. Now, let me write a return in order to give back the value of the rotational moment. And then I can close the function. And then if I run the function, I get here the computation of the rotational moment. It is, the eccentricity coefficient is minus 0.04. The length of the waterline is 117, so the Py was something like 510. If I make 510 times 117 length waterline times minus 0.04, I should get something similar, you see. This is the rotational moment. Now we have the wind forcing and the rotational moment. And then we can now compute the mooring forces. How to compute the mooring forces? This is interesting because, as I said, what follows, I mean, so far it's something that we can easily understand. Application of the formula to compute the wind forcing and application of a very simple law to compute the rotational moment. This is something that we can easily understand. Now, the decomposition of this wind force plus rotational moment into mooring forces along elastic lines, as I told you, is a classical procedure of structural mechanics, which requires quite a strong background, strong theory, I mean, quite a long theory of structural mechanics. I already mentioned to you, I'm not interested in this theory. So what I want to propose to you is a simple list of the analytical relationships that give us the solution. But I'm not interested in understanding why these relationships are justified and derived. Okay, I'm not interested in that. So this is something that, of course, it's a bit complicated. Let's try to just have a look of what we need to do, and let's have a look at the analytical relationships. And then we can apply them with the R code, okay? So let's read here. Computation, let me expand a little bit. Computation of mooring forces is a complex problem, as in general the ship is a rigid body with 3 degrees of freedom, which is berthed with elastic mooring lines. We refer here to the computation method proposed by the Department of Navy Naval Sea System Command. We consider the simplified case where the ship has 2 degrees of freedom only. Calculations are based on the following assumptions. The elastic modulus of the mooring lines does not vary with mooring forces, so it's a constant. Mooring line arrangement is symmetrical with respect to the y-axis. I go back to the figure, to the scheme. This is the mooring line arrangement. And you see that it's symmetrical with respect to the y-axis. Okay, good. Of course, this is an assumption. Yaw moment, MW, and lateral force, PY, wind force, are applied at the ship pivot point. The mooring lines are assumed to run horizontally. Okay, we can relax this assumption. And this is the step-by-step procedure. Take the coordinates of bits, end of the mooring line on board, chocks and bollards. The bollard is the end of the mooring line on the berth. The chock is the point through the ship where the mooring line passes on the side of the ship in order to connect the bollards on the berth to the bits on the boat. The mooring line should pass through the side of the ship. And the chock is the location of the hole. In the side of the ship, the mooring line passes through, okay? So we need to take the coordinates of bit, chocks, and bollards. Determine the horizontal length of each mooring line from bits to bollards. Determine the total cross-sectional area of each mooring line. This is the product of the rope cross-section times the number of parts per mooring line, normally 3. So the mooring line is composed by 3 ropes. So the total cross-sectional area of the mooring line is 3, number of ropes in this case, times the rope cross-section time, cross-section. Okay, perfect. Now, so in poor words, we need to know the cross-sectional area of the mooring lines. Now, determine the elastic modules of each mooring line from the producer. The rope has an elastic modulus. Determine the angle between each mooring line and the y-axis. See figure 1, the scheme that I have shown to you before. Determine the length of the mooring line between the chock and mooring bits, as well as the length between the chock and the bollard. Okay, here there is a picture of a chock. Okay, it's, I need to check where it is, but let's see, chock, ship. Here is a chock, okay, just to understand what we mean. Good, now, determine the total breaking strength of each mooring line. Determine the spring constant of each mooring line. Remember, they are elastic mooring lines. So this is the spring constant, which is a function of the section and a function of the elastic modulus and a function of the length of the mooring line. Determine the spring component in the y direction. So we have to multiply the spring constant times the inclination of mooring line with respect to the y direction. Determine the product of the spring component in the y direction times capital Xi, where capital Xi is basically what you see here, the y coordinate of the chock I. And then we have to determine this product. Take the following summation. Symbols have been defined before. apply now the wind forcing and yaw moment. And then we have to compute the ship's movement in the y direction, this formula. Okay. And then a rotation of ship around the vertical axis, this formula. And then we are ready to compute the force component for each mooring line with this formula. Compute the forces in the direction of the mooring line, this formula. And then determine the safety factor for each mooring line. Forcing should be not greater than break forcing divided by the safety factor. And Y may check the computation by verifying that each of the components of the mooring line in the direction of wind, of the mooring line forcing in the direction of wind, the sum of each component is equivalent to the wind forcing. Now, let's, yeah. On the, no, absolutely not. No, absolutely not. This is, as I said, something that we need to apply, but we, at the exam, absolutely not. Even, I would say that we don't even need to understand this, okay? Now, let me just get the whole, everything is done here. Computation of the length of the mooring lines, length from bollard to chock, computation of spring constant, etc. And then there is the output from this function. Now, let's copy the whole code into R. Copy. I paste here. 1 second, because it is, okay, good. Now I can make moorings. Okay, so this is what I get back from the code, PY, yaw moment, the component of the wind forcing in the direction of the mooring lines. And this is the forcing along the mooring lines. And then these are the checks that the safety factor is respected, and the sum of the Y component is equal to the wind forcing. Of course, I mean, this exercise, I think it is useful to give you an idea of what things are to be done. But given that we don't go into the details of the procedure, because as I said, it's a topic of structural mechanics, we don't need to learn the details. We don't need to learn the relationships. And we just use this exercise as something that helps us to understand how operationally things are to be done. I wanted to prepare this exercise for you because operationally I think it is useful. But on the other hand, it is something that you cannot remember by memory. And if you're interested in more details, there are the references in the page. Okay, any question? Okay, we have one thing left, which is the adaptation of the analytical formulation. Next time, I will get it back with more clarity for incident and reflected wave. Okay? I apologize that today I was a bit confused because I didn't remember the formulation well, and you know, I had a busy day. I didn't have time in the morning to because usually before lecturing I rehearse and I refresh my memory, and this helps in being clear. Otherwise, basically you run the risk of being not very clear. This is what you also have to do at the exam, I mean. And if you want to be very well prepared, of course, you need to refresh everything a short time before talking. Okay, thank you very much, and see you next Wednesday.